Good morning everyone. I thought we'd try something a little bit different this week. So what I'm going to try and do is summarise a topic. So today's going to be the ever-changing Earth topic. I'll talk you through some of the different parts of it, try and highlight key ideas and things like that, and then following the video or videos I'll set some questions from the past paper booklet. So you may find it helpful to have a blank piece of paper in front of you. You may find it helpful to have the revision guide in front of you. Entirely up to you what you decide to use. Just try and make it as useful as possible for you. So first thing is planet Earth. In the ever-changing Earth topic, the Earth is made of different layers. It has different layers as you move inside towards the core. You've got the crust, which is very thin and rocky layer, so it's probably the thinnest layer of the lot. Then you've got the mantle, which has some property. Some of it's kind of like rock, some of it's kind of like a liquid, so it's like a semi-solid, so it can flow around. So properties of a solid, if we say but it does flow. And that'll become important later on in the topic. You've then got the outer core, which is made from liquid, nickel and iron, and the inner core, which is made from solid, nickel and iron. So those are the different layers. You've got the crust, you've got the mantle, you've got the outer core and the inner core. Now the crust and the mantle put together, or particularly the outer part of the mantle anyway, are given a particular name, which is called the lithosphere. So the lithosphere, and that is where you find the different tectonic plates located. So it's this section here where we have the tectonic plates, and so these two outer layers are broken up into gigantic pieces, some very big pieces, some slightly smaller pieces, which are the tectonic plates that can move around. So lithosphere is the tectonic plates. Now I'm sure you'll have heard of Alfred Wegener already. So who was Alfred Wegener? Why did we learn about him? So Alfred Wegener talked about the idea that once upon a time planet Earth and all the land on planet Earth existed in one piece, and that piece, hopefully you already know, is called Pangaea. And what he said was, over time, Pangaea broke into pieces and formed what we know as the different continents today. Now, I'm not going to try and draw them, so it would take me forever, and my drawing skills aren't that great. So, they all broke apart from the original Pangaea. Why did he think this? What evidence did he have to support that theory? Well, there's three big key pieces of evidence that he uses, or that he used. One were that on the various continents where they were likely to fit together, so these two were likely to fit together here, there were similar fossils at the edges of the continents. So you got similar fossils, similar species of animals on the edges of the continents. You also got similar rocks on the edges of the continents. So similar rocks. There could either be the types of rocks, it could be the age of the rocks, or how the layers are put together. So similar rocks at the edges of the continents. And then the last one, which is the one that people tend to remember best, is that they fit together like a jigsaw. So he found that you could fit the continents together like a jigsaw. So that's what he supposed. He supposed they were all together once upon a time and that they've split up. These were his 3 pieces of evidence. The problem he had was explaining how those continents managed to split up to how we know it today. So time went by, and then eventually a theory came forward, which was the theory of continental drift, and more importantly, convection currents. So this theory that came about, which I'll explain in a second, was able to back up Alfred Wegener's claims and actually show how they once were together and now have moved apart. So how do convection currents work? So you've got these tectonic plates. Maybe if I draw a separate diagram, you've got the tectonic plates, which all are fitting together, broken into pieces in the crust and the mantle. And underneath them you have currents of molten rock, so magma, which are moving around. So the currents, the flow of the magma is moving around, and as the magma moves around, so these are convection currents, what will happen is the plates will slowly move, and that then results in the continents moving around. So what have we had so far? We got the structure of the Earth, the different parts of it. We've then got Alfred Wegener saying the Earth was all the land in the Earth was once all together. It's drifted apart. There is 3 pieces of evidence to back it up. His problem was he couldn't explain how it happened. Then later on it was found that it was actually convection currents underneath the tectonic plates, which would have moved the different landmarks around. Okay, so we're now going to look in a bit more detail at how the different tectonic plates move and what is called plate boundaries. You have 3 different types of plate boundaries. You have what is called a destructive, destructive plate boundary, where something is destroyed. You have a constructive plate boundary, where construction, where something is made, and then you have a conservative plate boundary. So conservative, you conserve it, nothing's destroyed, nothing's created, everything stays the same, but stuff moves around. So destructive plate boundaries first. That's when 2 plates move together. What happens when the 2 plates move together is the more dense plate, now this is usually the oceanic plate, so the more dense oceanic plate ends up, so if we look over to the after picture, going underneath the less dense plate. The term for that is called subduction. So the more dense oceanic plate is subducted under the less dense plate. As it is subducted, this part of the plate will melt to form magma. As it melts to form magma, you can kind of think of it as going to be pushing the magma that was already there up through the cracks in the rock, and that is how you get the volcanic eruptions from the destructive plate boundary. So plates move together, the more dense oceanic plate becomes subducted, it melts to form magma, and the extra magma then forces the magma up, and you get volcanic activity. The second type of plate boundary, as I mentioned before, is a constructive plate boundary. So that is when 2 plates move apart from each other. as that happens, so as the plates move apart, what will happen is the magma that was underneath will start rising up in the gap that's been created, and therefore you end up with volcanic activity. If it's under pressure, then it'll be more significant. Sometimes it can be very slow. As the magma rises, it will cool, so it will cool down, and as it cools, magma is liquid rock, so it cools to form new igneous rock. So that'll be happening up here. It'll come out through the volcano, travel down, and it'll form new rock as it cools, which is igneous rock. Same here, travels up, it'll cool along the top here to form new igneous rock. The final type is a conservative plate boundary. This is when the two plates, they don't move in or away from each other, they just move and rub up against each other. The friction as they rub up against each other, so you can see them moving in the diagram there, they've moved, is going to lead to earthquakes. So move together, destructive, destroying some of the plate, move apart, constructive, so making new rock, and then move side by side is going to cause earthquakes, which is a conservative plate boundary. Okay, so now on to looking at the atmosphere. There's three different sort of chapters to this. You've got the early atmosphere, you've got the current atmosphere, and then you've got the changing, how it's changing today. So the changing atmosphere, I'm going to call it. So early atmosphere. The early atmosphere was formed by volcanoes. Most scientists agree on this idea. So volcanoes, they released ammonia, so NH3, so ammonia. They released carbon dioxide, so carbon dioxide, and water vapour, so H2O as a gas, water vapour into the atmosphere. So the early atmosphere, the first atmosphere formed, contained mainly ammonia, carbon dioxide and water vapour released by volcanoes. Then over time, the atmosphere has changed slowly. I'm hoping you already know some of these things, but what will happen is the Earth will have cooled slowly, so it will have cooled down, and as it cooled down, the water vapour, so the water as a gas, will have cooled down to give us oceans. So we're going to get oceans forming. So we have less water vapour now in our atmosphere. As the oceans then formed, you get photosynthesizing plants. And the photosynthesizing plants, well, photosynthesis, they convert carbon dioxide into oxygen. So the CO2 becomes oxygen, so we have plenty of oxygen in our atmosphere, in today's atmosphere. Still got carbon dioxide, but there's far less carbon dioxide, so the level of carbon dioxide has gone down, the level of water vapour has gone down, the level of oxygen has gone up. The oxygen that was made would also then react with the ammonia, and that reaction will produce nitrogen. So we're going to get nitrogen being produced. You don't need to worry about how it happens, but the fact that we've got oxygen, the fact that we've got ammonia, Those then react together to give us nitrogen, so we've got loads of nitrogen in our atmosphere. That's the main gas in our atmosphere. And what have I missed? So that gets rid of the ammonia, the carbon dioxide levels have gone down, and the water vapour is condensed to form the oceans. Have I missed anything? I don't believe so. So, in our current atmosphere now, we have 78% of it is nitrogen, 21% is oxygen, 0.04% is carbon dioxide, and then I always forget this one, 0.9% is argon and other gases. So if you look, original atmosphere that was formed, ammonia, carbon dioxide and water vapour are the main gases. Now the main gas is nitrogen, which wasn't there before. Oxygen levels have gone up significantly, carbon dioxide levels have dropped significantly, and then 0.9% argon and other gases. Don't worry too much about what the other gases are, just that they are other gases. And then the final thing to think about with the atmosphere is how it is changing today. So because we are burning fossil fuels at a very quick rate, so we're digging up crude oil, we're burning things like petrol in our cars, we're burning other fuels like kerosene in aeroplanes, and in factories burning other fuels. What we're doing, so burning fossil fuels releases carbon dioxide, so it uses up oxygen and it releases carbon dioxide. So the level of carbon dioxide in more recent times, and let's say the past 100 years, is starting to go up. So yes, we still have the nitrogens, the oxygens, and things like that, but the level of carbon dioxide is slowly going up. It's not significantly changing in terms of the percentage, but actually small differences in the percentage make a big difference to things like the temperature of the planet, which I'll come to in a second. So yeah, it's important to understand that the atmosphere at this stage has been stable for millions and millions of years, and we've had these percentages for millions and millions of years. The reason that it's been stable is because of the fact that respiration, so animals respire, they take in oxygen and they release carbon dioxide, and then photosynthesis, the plants take in carbon dioxide and they release oxygen. Now, what's been the case over the past millions of years in our current atmosphere is these two processes have balanced out. So we've had the same amount of respiration happening as we have photosynthesis, and so these two processes are balanced out. What happens when we start burning loads of fossil fuels and we start introducing combustion into the equation is combustion takes in oxygen and releases carbon dioxide. So we've started doing that when we burn fossil fuels. We're disturbing the balance. We're also, because of deforestation, we're cutting down trees, and as a consequence there's less photosynthesis happening. So the atmosphere is currently changing, the levels of carbon dioxide are going up because we're burning more fossil fuels and we're taking in oxygen and releasing carbon dioxide, and we're pulling down forests, so less photosynthesis is happening. You could also add, because the population of the planet is increasing, there's an increased amount of respiration happening as well, and that's disturbing the balance too. So one other issue with burning fossil fuels is fossil fuels contain what are called sulfur impurities. So you might have a lump of coal, and inside it there'll be some impurities of sulfur. And what happens when you burn that lump of coal then is something called sulfur dioxide is formed. So the sulfur reacts with the oxygen that you're using to burn the coal to make sulfur dioxide, which is a gas. The gas will then travel up to where the water is in our atmosphere. So sulfur dioxide travels up to where the water is in our atmosphere. And once it comes into contact with water, it forms something called sulfuric acid. And then that sulfuric acid will fall as rain, and this is where we get the acid rain from. So you got sulfur impurities. When you burn the coal, it releases sulfur dioxide into the atmosphere. That then reacts with the water to give you sulfuric acid, which falls as acid rain. Problems with that is the acid rain lowers the pH of ponds, lakes and rivers. The ocean's probably too big to have the pH lowered by the acid rain, but it does have a significant impact on ponds, lakes and rivers, so it might end up killing plants, might end up killing some of the animals that are in there as well. It'll damage metal structures, so cause increased corrosion of metal structures. And then the final big impact is it will also damage statues, particularly those that are made of limestone. So yeah, the final part of the topic then is some little tests. Oh, actually, I forgot something. So because of the issues with acid rain, what some companies have started doing is in their chimneys, you can imagine them, they've got their fire here, they're burning the fossil fuels, and the sulfur dioxide is going up and out through their chimneys and up into the atmosphere. They've introduced something called sulfur scrubbers into their chimneys. And what the sulfur scrubbers do, it sounds fancy, but all they do is remove the sulfur dioxide and stop it being released into the atmosphere. So that's one step companies have taken in order to stop the effects of acid rain. Right, the last thing then, on to some tests for the different gases that we've come across in this topic. So you've got 3 tests in this topic that are worth knowing. Test for oxygen, test for carbon dioxide, and test for hydrogen. So how do we test for oxygen? What you do is you take a splint. Initially it would be on fire, but you blow it out so that it's glowing. So you'll see when you blow a splint out, it'll be glowing. If you put that glowing splint into oxygen gas, the splint will relight and give you a flame again. So the test is take a glowing splint and the splint will relight. Next, for carbon dioxide, what you do is, let's say you've got a reaction, awful flask, but let's say you've got a reaction and it's fizzing, so it's making carbon dioxide, but you don't know that quite yet. What you can do is you can funnel the carbon dioxide into a container filled with lime water, and it will bubble through the lime water. So the test is to bubble the gas through lime water, and the lime water will turn cloudy if you've got carbon dioxide present. So test 1, glowing splint relights in oxygen. Test 2, carbon dioxide, bubble it through lime water and the lime water will turn cloudy. And then the final test is for hydrogen. You take a lit splint, to the gas, and if hydrogen is present, it will go pop. And that is everything that you need to know pretty much about the ever-changing Earth topic. So what I suggest you do at this point now is you get your science surgery booklet, whether it's triple or double, doesn't really matter. The pages are the same and the questions are the same for both. I'd suggest you make sure you've done the questions for the ever-changing Earth topic, so pages 4 to 16 in both of the books, and then if you go on to Google Classroom, you will see the mark scheme for each of these topics. Do let me know if you get stuck on any questions, or if any don't make sense to you. Feel free to email me and I will help you.